Welcome to our chapter, Electrical Grid Scenarios. In this video we analyze the electrical grid and its topologies as major spatial flexibility option. Hereby we apply an energy system model for the region Europe, Middle East and North Africa, the EUMENA region. This allows us to see the impact for the energy system regarding an meshed overlay grid, border interconnections, transmission and distribution grid, as well as the integration of dispatchable solar power via point-to-point transmission. Therefore, we introduce a model which can represent the transmission and distribution grid. As an example, we analyze the electrical grid of Germany and evaluate grid expansion with different shares of fluctuating and dispatchable renewable energy. Finally, we show with scenarios the impact for the electrical grid topologies with an energy mix including a transfer of dispatchable solar power. For a future energy system of the EUMENA region, based on low carbon emission and minimal system cost, we use scenarios with sensitivities of techno-economic assumptions. The energy system is represented by a model with 15 nodes, including spatial distribution effects such as the transmission and distribution grid inside a model region. A model is a representation of an already existing, past or future original. Characteristics of the original considered as essential are emphasized. Aspects that are considered secondary are disregarded. In this sense, a model is a simplified image of the original reducing complexity. Thus, conclusions derived from models must be scrutinized with focus on the model assumptions. For an evaluation of the grid model, we use electrical grid topologies to assess their value for the energy system. These are point-to-point transmission for the transfer of dispatchable solar power, meshed overlay grid with unlimited capacity, and a combination of both, however, with limited border interconnection capacity. Each of the model nodes includes representative transmission and distribution grid characteristics. A point-to-point interconnection is an infrastructure which connects two precise points of a system. This can be a power plant and an off-taker. The chances are that point-to-point interconnection is projectable with specific producers and off-takers, thus a clear business case is possible, and a bundling of transmission lines can allow common infrastructure corridors. The challenge is that a transmission line expansion is needed inside a multinational structure. A meshed overlay grid is a possible future energy infrastructure which can transmit a high energy amount over a large distance without specific destination. The chances are that a meshed overlay grid can increase the overall reliability, balance renewable energy due to a large spatial expansion, and enables international electricity trade. The challenge is the high planning effort over a large area with a multitude of different authorities. Unclear financing and operation. The combination of existing grid and meshed overlay grid with limited border interconnection capacity and point-to-point transmission lines might result in the optimum with chances and challenges of both topologies. The chances are the combination of limited overlay grid, similar to existing transmission grid, and focused use of dispatchable renewable energy. The challenge is that new grid, existing grid and single transmission line expansion is needed. Good planning ability and high spatial flexibility of the energy supply might be the optimum of an energy transmission infrastructure. However, transmission line infrastructures are difficult to implement already nationally due to high planning effort and low social acceptance. Thus, the effort in building new transmission capacity should remain low, using as many advantages of point-to-point and overlay grid infrastructure as possible, which is only feasible in a combination.
In studies with a reduced node model, transmission and distribution grid are often neglected due to computational constraints. Grid constraints like regional capacity limits are consequently disregarded, leading to an overestimation of fluctuating renewable energy such as wind power and photovoltaics due to their energy provision according to supply. Therefore, we introduce a validated grid expansion model which characterizes the electricity grid expansion by the feed-in capacity of wind power and photovoltaics. We use a grid model of Germany with 491 nodes for the transmission grid to calibrate the model and additional specific grid cost for the distribution grid from literature. In order to have a universal model, we compare the approach to other continental European countries. The detailed results of the 491-node model representing the German transmission grid show the transmission line topology with installed link capacities in a case-specific grid. The cases are different shares of fluctuating and dispatchable renewable energies. Regional distribution of the installed power plant capacities is made according to their economic potential, respecting a cost-minimal approach. Techno-economic assumptions are available in the reference. The resulting annual cost of the transmission grid are between 9 to 19 billion euros, time value of money from the year 2015, depending on the share of fluctuating and dispatchable renewable energy. The higher the share of fluctuating renewable energy, the higher the transmission grid cost. High shares of fluctuating renewable energy, such as the 90-10 share, lead to a triplication of the national installed transmission line capacity, while the major impact arises from the HVDC north-south transmission lines. It can also be seen that some transmission lines are missing, light blue color, which indicates a concentration of the grid expansion in some regions, while other regions are not economic with regard to the energy system. Especially wind offshore causes a high transmission expansion due to the high transmission capacity starting at the North Sea. A balanced 50-50 mix also leads to grid expansion, however in more regional equal way. Therefore, needed international power kilometer are discussed in the following. New calibration approaches with higher spatiotemporal resolution can still improve the precision of the node internal grid model. The major achievement of the model is that it can represent the grid in cost, curtailment, and interdependencies, such as the use of fluctuating and dispatchable renewable energy shares.
In this analysis, the focus is on the overlay grid as spatial flexibility in the UMENA region. Therefore, two scenarios are applied. The scenario, unlimited grid, is based on the unlimited expansion of an overlay grid that connects regions in UMENA. Such a scenario implies a strong collaboration inside UMENA. The other scenario, isolated regions, excludes this overlay grid but still uses grid expansion inside the regions, applying the transmission and distribution grid model. Both scenarios apply a so-called greenfield approach, with an integration option of all established technological options of the analysis, including dispatchable solar power via point-to-point transmission lines, in short, CSP-HVDC, nuclear power plants, and carbon capture and storage, with a carbon emission limit of 16 gram per kilowatt-hour. The scenarios help to detect the influence of an overlay grid under a least cost optimization and an evaluation of multi-criteria for an energy system. The results with the integration of the overlay grid in red frame as well as its exclusion in blue frame. The figures illustrate with the blue lines an expansion of transmission lines of the overlay grid. Up to 85 gigawatts from model node northwest, NW, to model node west, W, can occur. Transmission lines are expanded more in north-south direction than in east-west direction. Interconnections between North Africa West, NAW, North Africa East, NAE, and Middle East, ME, are assessed as insignificant by the model. Both figures show the grid expansion inside the model regions. This grid expansion of the transmission and distribution grid shows in the scenario, unlimited grid, high expansion in some regions, and in the scenario, isolated regions, an almost equally distributed expansion in every model region. The power kilometer subdivision in the scenario, unlimited grid, shows that CSP-HVDC is not integrated using an overlay grid. The exclusion of the overlay grid leads to the integration of CSP-HVDC. However, the results of the scenario, unlimited grid, show that dispatchable power is built also for export from North Africa and the Middle East to Central Europe, however for a transmission via overlay grid. Also, wind offshore capacity expansion takes places and causes the high transmission capacity between Northern and Central Europe. Having a look on the evaluation criteria in the spider diagram, it is remarkable that the two scenarios do not distinguish much in system cost but in almost every other criterion. The use of the overlay grid is about 7% more cost efficient. Compared to the scenario, isolated regions, the scenario, unlimited grid, reduces power plant capacity to about 13%, storage capacity to about 272%, and curtailment to about 34%. However, it causes a significant increase of power kilometer with about 176%. Thus, small cost changes can lead to a recognizable change in all other parameters of an energy system. A least cost approach can therefore be helpful comparing scenarios with other evaluation criteria on the same least cost level. As shown in this analysis, alternatives are essential for a comparison of scenarios. Otherwise, a least-cost approach can also lead to misinterpretations if comparable alternatives and sensitivities are missing. As mentioned before, an unequal spatial distribution effect of regional transmission and distribution grid expansion arises, including the overlay grid. This effect also appears with power plant capacities. The model places the capacities in those regions where it is the most cost-efficient. Thus, some regions have a giant capacity of only few technologies, while in other regions some of today's already installed technologies like photovoltaics are totally missing. The consequence is a strong dependency of model regions. In both scenarios, nuclear power plants are not implemented due to cost-efficient alternatives. The option of the overlay grid is chosen in the scenario because it is more cost-efficient to balance energy over a spatial area than building electrical storages or curtail power plants. However, the need of such a large capacity expansion of power lines is arguable due to social, political, and organizational barriers.
Power kilometers are defined as capacity of an electrical transmission infrastructure and its length. A transmission of electricity over distance is a cost-efficient flexibility option. Using high shares of CSPH-VDC increases total power kilometer. An adequate share of CSPH-VDC leads to lower total power kilometer for some model regions. The regional transmission and distribution grid is expanded in the case of a higher share of fluctuating energy. In other words, the lower the dispatchable share, the higher the regional grid expansion. A scenario that includes CSPH-VDC reduces power kilometer of the nodal grid. However, as mentioned before, higher shares of CSPH-VDC can increase total power kilometer due to more needed CSPH-VDC point-to-point power kilometer. Thus, a trade-off arises between nodal grid power kilometer and CSPH-VDC point-to-point power kilometer. An adequate CSPH-VDC share is therefore essential to reduce total power kilometer. The operational behavior of the grid is influenced by the capacity limit of transmission lines. The more often the capacity limit is reached, the higher the stress for the grid and the more often is the potential intervention by the transmission system operator. Reaching capacity limits of the transmission lines is analyzed by numbers of peaks in the grid. Including CSPH-VDC reduces such peaks up to 29% and therefore the grid stress. Reducing peaks leads to fewer possible bottlenecks in the grid. Consequently, CSPH-VDC allows a better application possibility of the grid. Dispatchable solar power is technologically ready for use and its elements are in operation worldwide for many years so far. The important point of view is that CSPH-VDC include a high-voltage transmission line. Therefore, it has to be considered as a power plant in distance, just with a long transmission line from the generator to the feed-in point into the grid. An expansion of point-to-point transmission lines and the existing grid is better projectable and more concrete for a business case than just outlining a meshed overlay grid. Thus, dispatchable solar power, its transmission from desert regions can provide value for the energy system as one major supplemental component. In the future, a reinforcement of the transmission grid with additional point-to-point lines can be implemented at first, and then an enforcement of both infrastructures might take place, leading to a meshed overlay grid still including point-to-point transmission lines. The first informal law of ecology says, everything is connected to everything else. Feel free to follow and contact us via social media or email.